All right, well, let's see. You have a little handful of proofs to do today, right? And didn't I get, I think I just gave, I might as well put this on camera. Which one did you say that you wanted the hint on? To prove number 34, which is expansion of until. Want a little guidance with that one? What I recommend you do is start with the left-hand side, which is the simpler side, and use the definition of eventually, so it's defined in terms of until, and then go ahead and expand until. And I think it'll just fall right out. Did that work?
Yeah.
You already got it? Yeah.
Thank you.
Mm-hmm. Now, I did want to say another thing, too. Did you guys get your email notices when I got your last programs done? Because a number of people did not actually translate the algorithm from the binary text. So whenever, especially this is more difficult with Java, because with C++, it's easy just to, it's almost kind of like a one-to-one translation, and you don't have all of this run with the process ID and all that kind of stuff. And some people kind of got that process ID thing not working quite right. And well, one thing is, the process ID is supposed to be a single integer that is set in the constructor for the process, and you should never monkey with that. You should never change it. Okay, so that's the identification that sticks with that processor the whole time. And also, a couple people didn't have a wants P and a want Q. They just had a single want. So, but in order to translate that second attempt, there was a want P and a want Q. So you needed to do that translation. And then I think, is today's assignment the one to do Dekker's algorithm, or is that next time? But it's just a straight translation. If you look at my solution, if you had problems translating that second attempt and you look at my solution, you can see kind of like the general way to do a translation into Java. That's yet another example for how to translate into Java. Okay, so any more questions about the homework that's due today? Okay, good deal. Well, you can hand those in at the end of class. Looks like, oh, we have some data structures here we need to get rid of. Sure.
For number 60?
Yes.
I'm not even sure if I started it right.
What is, okay, so the question is about how to prove number 60?
Yeah.
And what is, can you tell me?
Always P equals
Always P equals always P.
Yeah. And I got it to always not, parentheses, true union not P. Is there a way to like get the not to go across?
Yeah, well, now, I'm just thinking off the top of my head. Has anybody solved this not by going to the definition, but by using duality? Is it pretty straightforward that way?
Yeah, well, the first step, I pulled a rabbit out of the hat.
Yeah, you pull a rabbit out. What do you make this?
I made it not P.
Oh, you made yes. That's. Oh, you started with the left-hand side.
Yeah.
Oh, that's a good idea. Did you hear that tip? Start with the left-hand side, pull a rabbit out of the hat, and make this always not P. Then you can mess with the knots with the always and the not, which would give you the.
I made it always not eventually not P.
Yeah, that you use duality with eventually to flip to. Oh, that was a good tip. Okay, then can you manipulate?
Isn't that the same as using the definition, more or less? 'Cause then
Oh, sorry, that is the definition. Yeah. I was thinking of, oh, yeah, I was thinking incorrectly. I was thinking about the definition for until. I was thinking about the definition of eventually, which has an until. But this is defined in terms of eventually. But did that help? Does that help if you...
I'm not really sure where to go. Well, I know that then you would turn it into an eventually with the...
Yeah, and then can you do it...
Always, but then I don't know where to go.
Yeah, well then can you do it again? Can you keep doing it? Because I probably what this is, probably what can you get it to where you have an eventually? Is that what happens?
That's what I got.
You get it to an eventually, but then you know that eventually collapses,
Okay.
and then you move it back. Is that working now?
The like nots and eventuallys and always,
Mm-hmm.
they don't need parentheses if they're all in the row, right?
That is correct. So that's a good point, and the answer is yes. That is correct. The observation is if you have a whole string of nots and eventuallys and alwayses, all strung together, they are all unary, which means by definition they're evaluated right to left, and you don't need parentheses. It's right to left. But because they're all together, I mean, you don't need parens. Yeah. And they also, all of those, they're higher precedence than any of the binaries. Right? So. Okay, are we good? Well, these are good questions. Okay, so what we're going to do today is we're actually going to use this stuff. And it's going to take practically the whole, it's going to take, at least half of our time today. It's the verification of Dekker's algorithm, right? And we're going to use some of these tools that we've been learning with this linear temporal logic. Now, let me just sort of warn you that this proof of the correctness of Dekker's algorithm is quite complicated and involved. And what I've done is I've taken the narrative from our book and I've created this set of slides that walks us through it in quite a bit of detail. But there's so many ideas, and the logic is so dense when you talk about it in English, it's very difficult to follow. But I think if you have this set of slides, by the way, I just updated these slides just today, just a few hours ago. So you might want to re-download this if you're going to be taking notes on the slides. But what I recommend you do is you use the slides to understand how the proof goes, because there's a lemma and then there's a lemma of a lemma, and it gets quite involved. But I think we'll be able to get through it. And here another thing, I'm not going to ask you to prove Dekker's algorithm is correct on the exam. It's too long and too complicated. Best I could do would be but you need to understand it. So best I could do would be to ask you about a step or two or something like that. So you need to study it to understand how it works. Okay, with that in mind, here we go. First of all, what are the three things that we need to prove to show that to solve the critical section problem for any proposed solution? What are the three attributes, or one of the three things they have to have? Mutual exclusion, no deadlock, and no starvation. Mutual exclusion, deadlock-free, starvation-free. But, okay, so now, on the other hand, if we can prove starvation-free, then we have done what? Then we prove deadlock-free. So that we can just prove that stronger one. So what we're going to do, what I want to show you here is, not show you, but indicate what you're going to do, is, first of all, let's take care of the mutual exclusion problem. All right? And then we'll do the starvation-free problem. So here is a listing of Dekker's algorithm. We got want P gets false, want Q gets false, turn gets integer, turn gets 1. And we've discussed this before. So this all looks familiar, right? And here is how, and what you're going to do is you are going to prove mutual exclusion. Now, did you guys, I think we already had an assignment where you had to prove mutual exclusion once before, did we? Or no? Or maybe we proved mutual exclusion of, I think we proved mutual exclusion of one of those attempts. Okay. Was it the third one? Okay. Yeah, one of those, yeah. Okay. So this is going to be the proof of mutual exclusion of this is going to be very, very similar. It's going to be quite similar. It's based on what our author numbers Lemma 4.10. And here is his lemma. It has 3 parts to it, 4.2, 4.3, and 4.4. The first part is turn equals 1 or turn equals 2. Yeah?
Do you find lemmas like this by an exhaustive inspection?
You find them because you need them in order to prove what you want to prove.
I mean, in order to use them, do you have to do an exhaustive inspection of the code?
Oh, in order to prove each one of these lemmas?
Yeah.
No, well, yes, you do exhaustively look at each part, but you only pick, but you can be by looking at all of them, you can select, you can reason only those statements that will change them.
Okay.
Because how do you prove each one of these? How do you prove that each one of these is invariant? You prove what? How do you always prove it? So actually here, let's just talk through them. First it's turn equals 1 or turn equals 2. The next one is P3.5 or P8.10 equals want P. And the next one is Q3.5 or Q8.10 equals want Q. Well, obviously 4.3 and 4.4 are just symmetric. So all you have to do is prove one of them and then say the second one is similar with P replaced by Q and Q replaced by P. Are you with me? So you only have to prove 2 things. But how do you prove any invariant?
You put as true
True, you
for the loop. And, after each
Yeah.
iteration of the loop.
well, yeah, but in general, if there's not, I mean, proof by what technique is what I'm asking.
Oh.
Mathematical induction. And then what's the base case?
Turn gets 1.
Well, I mean, in general, what is the base case? What do you take as the base case in general? The what state? You take the initial state. Remember how that worked? So what you do, you take the initial state, you prove that so that's the base case. So you write that out, and then you see what the initial state is, and you show that that's true in the initial state. Then what do you show? And now comes your inspection thing. Then what do? You inspect each one of these lines, each one of these statements, and you see which one can possibly do what? Change the value of what it is that you're trying to show as invariant. And those are the only ones you have to consider. Are you with me? And then you assume that it's true in one state, and you show that if that one executes, it stays true. But you can narrow it down that way. Are you with me? Obviously, the only thing that can change turn, the value of turn, is an assignment statement that has turn in it. So you don't have to worry about any of the other ones. So you see what happens when that, yeah? And so here's a little assignment. It is an exercise for the student to prove these lemmas and to use them to prove that Dekker's algorithm satisfies mutual exclusion. Okay? And I think if you go back to that one that we were saying that one of those earlier attempts, we actually did that in the first or second chapter, or third chapter. Third chapter, yeah. In the third chapter, we actually did that. We actually proved that one of those satisfied mutual exclusion by doing this kind of an argument. So you just follow that same procedure. All right, so that one we'll leave up to you. Now starts kind of an involved logical argument that has several parts to it. But I hope that the way we've laid it out here will make it each step exceedingly clear. So here we go. First of all, so what we want to do is we want to prove, this is a proof of starvation-free, that Dekker's algorithm is starvation-free. Now what I've done is, what we're going to do is, these slides are going to have the proof steps over here on the left, and we're going to just have a picture of the code. the code, there's a code for P, and then there's a corresponding code for Q. So depending on which one we need, we'll either have the P code or the Q code over here, right? Are you with me? And this is proof of starvation-free. But now, to prove starvation-free, we're going to have a number of assumptions. And here they all are. So try to follow this now, you guys. First of all, we are going to assume that all assignment statements progress. That's number one. Now, what do we mean by progress? We mean that if you're at P2, that there's no problem assigning want P to true. We'll progress to P3. Are you with me? So that's an assignment statement. P5 is an assignment statement. P7 and P9 are assignment statements, and so is P10. Are you with me? So all assignment statements progress. Here's another assumption. Now we're using our notation from linear temporal logic. What we are saying, do you remember how we said that in order to be reasonable, we have to assume that if one guy gets in his critical section and he hangs up in the critical section, well, then all bets are off. That's like if an earthquake happens and the ceiling falls down on your computer, There's nothing you can do to prevent that. I mean, if that happens, then, you're not going to blame the, yeah, exactly. Yeah, you're not going to blame the solution. Okay, so if you're in P8, we'll eventually get to P9. So what that says, so how do we say that? We say that always P8 implies eventually P9. Now, do you see how that says in symbols what that means, right? Always P8 implies eventually P9. So if we're in P8, it's always the case that we will eventually get to P9. Okay? Now the third one. Now this one seems to sort of like go against what we're trying to do here, because this one says, if you're in Q1, you will eventually get to what? If you're in Q1, you will eventually get to what? Q2. So what we're saying is, for this argument to work, one of the processes cannot hang up in Q1. But this kind of seems like it sort of defeats the whole purpose of having it be starvation-free. Okay? But it turns out, because we said, to be starvation-free, you got to allow one of the processes to hang up in its non-critical section, and it still has to be valid. Well, it turns out that if you do assume, Dekker's algorithm is still correct, even if you don't make this assumption. But for now, for ease of analysis, we're going to make that assumption. All right. So now this is called our author calls this the progress assumption, PA, and it's always eventually not Q. Now, what does always eventually mean? What does always eventually mean about the thing? Always eventually means it can do what? It's always eventually, it could what? Oscillate, but it has to oscillate up and down forever. Okay? So this says always eventually not Q1. So that means that, does everybody see that this is the progress assumption? This is equivalent to the progress assumption. It's always eventually not Q1. So we'll get out of Q1. Eventually, we'll always get out of Q1. See? On the other hand, eventually always Q1, like if you eventually get into Q1 and you're stuck, you can still prove that Dekker's algorithm is correct, but that's left as an exercise for the student, which fortunately for you is not, the student does not include you. I'm not assigning that. So anyway, all right, that's for some other students, lucky students. Okay, and now the fourth assumption is P4. Now check this out. P4 and always turn equals 2 implies eventually P5. Now let's unpack this. What does P4 mean? That means here, this arrow, that means we're at P4 and we have always turn equals 2. So here we're at P4, and if we always have turn equals 2, right? That implies eventually what? We'll eventually get to P5. Because what is P4? If turn equals 2, right? Now here's the thing. This is in fact true and it's reasonable, but you got to be careful because look, neither of the following is true. Now let's see if we can think about this really hard. You see how this says P4 and always turn equals 2? What's the difference between that and this? P4 and what? Turn equals 2 implies eventually P5. This isn't true. This is true. Our original 4 is true. But this P4 and just plain old turn equals 2 implies eventually P5. That's not necessarily true. Because what could happen? You could enter. Does everybody see that by that interleaving, that is will not necessarily happen because P4 says this one is about to. When we say P4, we mean that the next time P is picked, P4 is the one which will execute. But just because that's the case doesn't mean. Doesn't mean that by the time it gets picked, turn will be 2. See, because of the interleavings. Okay, so that's our. So we will come back in the proof. We'll come back in our proof of correctness. We'll come back and we will quote these. We will quote these as we need them. And now here, oh man, I hate to put this on film. I hate to put this on film because this is the progress proof rule. Eventually, always A, and always A implies eventually B implies eventually B. This is the one that. What number is it on our equation sheet? 78? This is the one where I had a proof of it, and then I just recently discovered that the proof was incorrect, and so now hasn't been proved yet. And we've had some close ones, but if you can prove this one, I'll be eternally grateful. And not only that, you'll get 100 homework free bonus points. But our author says it's true. I believe it, even though I can't prove it yet. So anyway. Well, he has proved, well, actually, it's an assignment. Our author assigns it, and he says, prove that this is true. But he doesn't use the equational deductive system. It's just verbally. And we can prove that this is true verbally, right? Because look, what does it say? It says, now what does eventually always A mean? It means sometime in the future, eventually what? A will always be true. Well, if A is always going to be true eventually in the future, and furthermore, if always A implies what? Eventually B, then don't you see that eventually B has to be true. So I know it's true. It's frustrating to not be able to prove it with our theorems. But that's just our little system that we've set up. So I have confidence that this is in fact the case. And then our last assumption is all computations are weakly fair. Are we good? And similarly for P, Q replaced by QP. Yeah? Because this is just half of the coin. Okay. Now, before we prove starvation free, now here's going to be our approach. Here's going to be our style. Sometimes we'll prove the lemmas first. Sometimes we'll prove the lemmas second. This one we're going to prove the lemmas first. We're going to prove this lemma first. Then we're going to prove a couple of other lemmas later. So it gets kind of involved, but here it is. Lemma 4.11. If P insists on entering, eventually Q will let it. Now I know this stuff is hard to follow. Can be, but think about this as we go through it. If P insists on entering, eventually Q will let it. Now you remember how the want P and the want Q worked? Okay? So if P insists on entering, so if you insist on entering, you set your P, your want to true, right? So here is the lemma. It's L 4.11. Always want P and always turn equals 1 implies eventually always not want Q. Now do you see why that means Q will let it? Q will let it means not want Q. So So this lemma is, what this lemma is going to prove, what we're going to prove in this lemma is, if want P, if we have always want P, and we have always turn equals 1, that implies eventually always not want Q. Yeah? So we will need this in our proof later. So let's prove it. We're going to assume the conjuncts of the antecedent. Remember how that works? This is deduction. How do you do assume the conjuncts of the antecedent? Which one do you start with?
The right side.
Yeah, you start with the right side. You start with the consequent, and you prove that it's true, and you use what? Each one of these as if they are what?
True.
As if they are theorems.
Do you have to use all of them? Like, what if you're able to do it without using?
You know, that question comes up a lot. The question is, do you have to use all of the conjuncts to prove? And even the answer is, even if you only use some of them and not all of them, you have still proved it.
Okay.
In fact, you've proved something stronger.
Okay. And then, can you have it imply true, or does it have to equal it?
It has to equal true. Anyway, okay, so we're going to assume the conjuncts of the antecedent. So what do we start with? So tell me, what do we start with? What's going to be written down next?
Eventually always not want Q.
Yeah. Oh. Yeah, I was going to say the same thing. Eventually always not want Q. All right. So anyway, we're going to start with Q1 in the initial state. All right. And that implies, well, yeah. I think we'll see as we progress. Because on the left-hand side we have want P and turn equals 1. On the right-hand side we have want Q. So this is the listing for Q. And so let's suppose that Q1 is in the initial state, right? Q1. Now by our assumption 3, Q1 implies eventually Q2. What will happen? What do we know? That we will get to Q2. Is everybody with me on that? Okay. So that implies eventually Q2. But now that we're here, what do we know about statement Q2? What kind of a statement is that? Assignment statement. And so we know by our assignment progress that that's going to be eventually Q3. Are you with me? And now, what about now what's one of our conjuncts? Always want P. So but if we're at state 3 and we have always want P, then this is true, right? So what happens? So that implies what? Q4. Are you with me? Is everybody good? And now that we're at Q4, if we're at Q4, but we have one of our other conjuncts is always turn equals 1, so turn equals 1, so that will get us to what? Q5. And on Q5, the assignment statement progresses, so what does that give us? Eventually Q6. Are you with me? And then what about our conjunct always turn equals 1? So where are we now? If our conjunct turn equals 1, so but this is a wait what? Turn equals 2. So therefore what do we have? So what do we have? Eventually always Q6. Is everybody with me on that? So because we eventually got to Q6 and under these assumptions, always want P and always turn equals 1, we will be there forever. So eventually always Q6. Is everybody good? Okay. So now we have eventually always Q6. And so there we are at Q6. And now let's use our definition. Do you remember what the definition of Q3.5 and Q8.10 is? Or Q5. That's exactly right. It's Q3 or Q4 or Q5. Now where are we? Where are we now? At Q6. So do you agree then that means that we have and Q6 is not Q3 or Q5 or Q8 or Q10. Are you with me? Q8 or Q9 or Q10. Are you with me? So do you agree then that if we have eventually always Q6, we have eventually always not Q3.5 or Q8.10? Are you with me on that? Because we're at Q6. So we're not at Q3.5 or Q8.10. So we're always, so we are eventually always not this. Yeah? Okay. But now by 4.4, what did we say? Q3.5 or Q8.10 equivales what? Actually, this is one of the ones you're going to prove. That equivales what? Like Q. So can you tell me what's going to come up next? Yes. Eventually always, eventually always not want Q. And there you have it. Boom.
So did we do true simplification?
Actually, yeah, you're right. You are right. Well,
We started with the initial state. Which I guess is true.
yeah. Oh, that's a good question. We didn't, yeah. Yeah. We didn't start with the right-hand side and get it to a previously proved theorem like we normally do. Yes, you're right. It wasn't our traditional deduction style. Okay, is everybody with me on that? So there's our lemma. So now we can put this in our hip pocket and call it up when we need it. Okay, you guys. So what does it mean to be starvation-free? Look, what does it mean to be starvation-free? It means P2 does what? To be starvation means we can eventually get in, right? So it means P2 does what? Implies eventually P8. If we're at P2, we will eventually get in. We will not starve. So does everybody see that? This is what we have to prove that it's starvation-free. Right? If we're at P2, we'll eventually get to P8. Is everybody good? Now comes the lemmas on the lemmas on the lemmas. This is going to be proof by contradiction. How do you prove by contradiction? You remember how to do proof by contradiction? Yeah, well, you take the not of what you're trying to prove and you show that that's false or that it leads to a contradiction. Are you with me? Okay, so if we're trying to prove this, what will we start with? If we're trying to prove this, what will we start with? Not P2 implies P8. And we'll show that that leads to a contradiction. Are you with me on that? Okay. So, but now comes some, now you'll like this part. You will like the next few steps. Look, you guys, our old friend 3.59. Can you tell me what that is? Remember 3.59? Well, this is 3. I've written it out here for you. This is 3.59. So what is this? So what's the next line? Well, but what about this? And what about that not out in front? Yes. So it's going to be not P2 or eventually P8. And now is your chance. So now what did you say should come next, probably? De Morgan's, probably. De Morgan and double negation. So what will that give you? P2 and not eventually P8. Are you with me on that? Okay. So what do we have? P2 and what? Now this little dashed line, we have P2 and what? Not eventually. See that dash dash, that means not eventually P8. See how to interpret my little graphic there? Okay. So De Morgan and double negations is P2 and not eventually P8. And now comes a lemma that we're going to prove later. But let's assume it for now. Our style now will be to prove the lemma later, second. This lemma says that P2 and not eventually P8 implies P3, P4 forever. Now what do we mean by P3, P4 forever? We mean looping right here. Now how can you loop here forever? Because this is while want Q, so want Q is going to be true, and then turn is not going to be 2, so it'll come back here and it'll come back up to here and it'll be P3, P4, P3, P4, P4. Are you with me? So I'm claiming, we will show in a minute that lemma 8 implies this. So using that lemma, we have P3 and P4 forever. So just think of that as just spinning around here. Want Q being true and turn equals true being false. So we don't do this. We just spin right here in P3. So this is kind of like the key idea of proving starvation free with Dekker's algorithm. It's this P3, P4 forever. So continuing on, we have P3, P4 forever. Okay, I'm just continuing the argument from the previous. Okay, P3, P4 forever. Now, check this out. What do we know about P3.5 or P8.10? That equivals what? That equivals want P. Now, where are we if we're in P3, P4? I mean, what is this if we have P3, P4? Yeah, if this is looping forever, then that's true. So that means we have what? That means we have what? We have want P, right? So what I'm claiming then is that all, and if that's looping forever, that means we have always want P and we have always turn equals 1. Now why do we have to have always turn equals 1? Yeah, because it's never getting past here. If this is looping forever, turn has to be 2, right? And so it's okay. So turn is never 2 because the only place turn is set to 2, the only place turn is set to 2 is here. Yeah? So
if P3 and P4 is looping forever, isn't want Q true? Because while want Q.
yes. Yes. Want P.
Have want P.
Yeah, but want P is independent from want Q, isn't it? Because they're two different ones, and they can both want to get in at the same time. Unlike turn.
Yeah. So that why what prompted us to say that we do have want P though? That want P is true.
Well, we know that it's true. We know that it's true because we're in P3, P4. That's what this is telling us.
Okay.
Okay? And now isn't 4.11 the one that is 4.11 the one that we proved initially? And what did it say? Always want P and always turn equals 1 implies what? Eventually always not want Q. Okay, so that gives us eventually always not want Q. But wait a minute. What about P3? If we have eventually always not want Q, what's our P3? What's our P3? They can only loop forever if it's what? Is true. But if we have eventually always not want Q, that means what would happen? We'd break out of the loop. But that's not P3, P4 forever, and that's our contradiction. You see how that worked? Is everybody good with that? Okay, so now is all we have to do. Now, unfortunately, there's two more lemmas. There's this lemma, and then for lemma A, we're going to use a lemma B, and then we're going to have to go prove lemma B. But like I say, the argument is very dense. And I tell you, to read this in English is really is really, you got to think real hard. So I hope this helps. All right, so let's check out Lemma A. And here we're going to use some nice linear. We're going to use some nice linear temporal logic. So here is our Lemma A that we had to prove. We had to prove that P2. Remember, this is our depiction. Remember that a few minutes ago. We said P2 and not eventually P8 implies P3, P4 forever. That's what we have to prove. Okay, we have to prove that. That if you get here and you don't get to here, if you are here and you don't eventually get to here, that means you got to be spinning in P3, P4. I call that P3, P4 forever. Okay, now here's the way it works. First, let's do P2 and not eventually P8. So we're starting with the left-hand side. P2 and not eventually P8. P2 and not eventually P8. Well, now we're going to have another lemma, but that's coming later. Okay, so accept it for the next 5 minutes. Accept this lemma. P2 and not eventually P8 implies what? Not always turn equals 2. All right? That implies not always turn equals 2. And we'll show that when we do Lemma B. So therefore, if you accept that, we have not always turn equals 2. But now you guys, what about this? Now I know you know what the next line is. By the dual, what is not always turn equals 2?
Eventually not.
Yeah, eventually not turn equals 2. Okay, so so we have eventually not turn equals 2, right? But what do we know? From 4.2 we know turn equals 1 or turn equals 2. So therefore, eventually not turn equals 2 means eventually what? Yes, eventually turn equals 1. Is everybody good with that? Okay, so that's our first point. Now what's our second point? P2 and not eventually P8. Now, you see here, P9 follows P8. Are you with me? So if we have P2 and not eventually P8, but P9 is the only way we can get through P9 is through P8. So what does that mean? We have P2 and what? Well, what do we know about P9? P9 follows P8. So therefore, P9 never exists. But what is P9? But what is P9? P9, only P9 sets turn to 2, right? So therefore, only P9 sets, so turn is never set to 2. So therefore, what do we have? First, we have that P2 and not eventually P8 implies turn equals 1. Second, P2 and not P8 implies turn is never set to 2. Therefore, what do we have? Eventually what? Always turn equals 1, which is what we were trying to prove. If these loop forever, eventually always turn equals 1. Is everybody with me? So the only way P cannot reach P8 is if P3, P4 forever with turn equals 1. And now, coming into the home stretch, that's all we need to do now is do Lemma B and then we're done. Okay. Here comes Lemma B. P2 and not eventually P8 implies not turn equals 2. Not always turn equals 2. So here we have P2 and not eventually P8. We are claiming that what we used in our previous lemma was that's not always turn equals 2. And the proof of this is going to be by contradiction. So what we'll do is we will assume that we will assume that always turn equals 2. But look, if always turn equals 2, now let's progress. If always turn equals 2, then what's going to happen? We'll progress by code inspection. So what happens? This will happen, right? Are you with me? So that progress will be made, okay? And then, so want, and what about want Q? Okay, so now, but now if turn equals 2, then what happens? But this is we're assuming that always turn equals 2, so then what happens? So then what will happen? We get to P5, right? And then what will happen by assignment statement? Then what will happen? We'll get to P6, right? But then what will happen? Now we are at P6 and we are awaiting turn equals 1. Okay, so therefore what we have is eventually always P6. But by 4.3, P3.5 or P8.10 equivals want P. So what do we have, like we did before? Eventually always not want P, right? So, but now if we have eventually always not want P, now what happens? But now we can do progress by code inspection. Now this one I didn't, here, just check it out. This one we will progress by that assumption that we're going to make progress in the non-critical section. This is a assignment statement. Will progress. This 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 will progress, and this will progress, and boom, we'll eventually get to Q9. But Q9 does turn gets 1, and therefore eventually turn equals 1. So, but that contradicts always turn equals 2. Well, I know that's long and involved, but I think it's all laid out, and I encourage you to study it. And like I say, I'm not going to ask you to do this, on the exam. But this is how we apply linear temporal logic to proving correctness in concurrent programs. And if we had like a whole course on concurrency, we could delve into all of this stuff a lot deeper, but we are just presenting the ideas and doing a few examples of each thing. So now what we're going to do next time, tomorrow, is we're going to start, we'll go to the next chapter, and we're going to start, do you remember that question that you had when we were talking about spin locks? You don't remember the question? You asked me such a great question, and now you don't remember what you asked me about spin locks. Remember? Yeah, the inefficiency of spin locks. What we're going to do tomorrow is we're going to see, yeah, that's exactly right. We're going to see how to use a different approach from spin locks to solve the inefficiency problem of wasted cycles. Yeah. And those are called previews of coming attractions. Those are called semaphores. All right. Good deal. See you tomorrow.